Dear students, today we will see the new lecture, that is a higher frequency response of the circuit. So first you want to know, see over the set of different ranges of frequency, there is a limitation in your gain. So that is called roll-off function. In the low frequency, the roll-off function exists because of your coupling capacitor and the bypass capacitor. So in the low frequency part, so let me draw the graph. Okay, let me draw the graph. See, this is your frequency response, right? So here you will be drawing a frequency response like this. Okay, so this is a low frequency and this is your higher frequency. This is the frequency versus gain. See, in the low frequency there is a limitation of gain. This is called a roll-off. This is called a roll-off. Similarly, here it's called, here in the higher frequency it is called a roll-off. So what you want to understand is, this is a cutoff frequency and this is your cutoff frequency. This is a higher cutoff frequency, the lower cutoff frequency. So in the lower frequency part, your coupling and bypass capacitor will be considered in the equivalent circuit. Okay, so your stray capacitance, transistor capacitance, load capacitance will not work. Okay, you will not consider the model, that will be act as an open circuit. Okay, in the higher frequency analysis, your coupling capacitor and bypass capacitor will be act as a short circuit, and stray capacitance and transistor capacitor and load capacitance only will be considered in the model. That means what you want to understand is, in the low frequency there is a limitation of gain because of the coupling capacitor and bypass capacitor. In the higher frequency analysis, there is a limitation of gain because of the stray capacitance, transistor capacitor and load capacitance. So in the low frequency analysis, something circuit will be a resemblance to the high pass filter. Okay, in the higher frequency analysis, the circuit is something resemblance to the low pass filter. Okay, so in the mid frequency, the gain will be stable. The gain will be stable. You don't have any roll-off function. That means your coupling and bypass capacitor will be act as a short circuit, and stray and transistor and load capacitance will be act as a load circuit, will be act as a open circuit. Okay, this you want to understand. Okay, with this information we will go to the hybrid pi model for the higher frequency analysis, that was expanded model. Okay, first I'll give the idea how to understand from the transistor. So then I'll teach you the exact expanded model. Okay, let me first draw the transistor. You know that in between base and emitter forward bias, and in between base and collector is reverse bias. Okay, so in between base and emitter, you know that you have a forward resistance. Okay, that is called R pi. In between base and emitter, you know that you have a forward capacitor, that is called C pi. So understand that pi is nothing but a P dash E, mu is nothing but a B dash C. Okay, so this is for your understanding. Okay, similarly when you come to the base and collector, it is a reverse bias. Okay, so you have a reverse resistance. Here you have a reverse resistance, that is R mu, and reverse capacitance C mu. That's all. Now in the higher frequency analysis, this is external base and this is internal base. So in the higher frequency analysis, you will be having the material resistance, that is external and internal. So in between the external and internal, there will be a resistance that will be very few ohms, that will be considered in a higher frequency analysis. Okay, that like you have some 5 ohms or 10 ohms like that. So it will be given with the parameter of RB. Similarly, here you have a resistance called RC, that is the external collector and the internal collector, C dash E dash. Similarly, here you have a internal emitter, that is REX. Okay, you know that here you have a gain GM times of V pi. Now you consider early effect. So when you consider the early effect, in between collector emitter, you have a resistance R0. That everything we discussed in the earlier classes. Then I am bringing another capacitance, that is in between the collector and the substrate. So it is given as a CS. So I will repeat again. R pi is called forward resistance, that is a diffusion resistance. C pi is called diffusion capacitance, and C mu is called reverse resistance, and C mu is called reverse capacitance, that is a transition capacitance. So the forward bias will be given with the subscript value of pi, that is nothing but a B dash E, and reverse bias with the designated with the value of mu, that is nothing but a B dash C. And between the external base and internal base you have a resistance in the higher frequency part, that is given by the variable RB. Okay, so RC, that is a external collector and the internal collector. Similarly, external emitter and the internal emitter REX. Then current gain factor GM times of V pi. Then R0 is a early effect resistance. Then CS is the capacitance between a substrate and the collector part. So this only I am going to convert into the model. Okay, this only I am going to convert into the model. Okay, so it will be very interesting. See how I am going to convert into the model. Okay, so you consider this is a network 1, this is a network 2, and this is your network 3, and this is your network 4, and this is your network 5, and this is your network 5, and this is your network 6, and this is your network 7, and this is your network 8. That's all. Okay, so like I am going to first I can write like a I'll draw the model. Okay, so let me erase this. Okay, so how I am going to draw? It will be very simple. First I will draw, then I will show you the expanded model of your hybrid biequivalent. So first, this is a emitter, right? So this will be a base and this will be a collector. Okay, so first let me put for the forward bias, that is R pi. Okay, then capacitance C pi. Here you have a reverse capacitance C mu. You have a reverse resistance R mu. Then you have an internal base resistance RB. So this is a B dash. Okay, similarly here you have an internal collector resistance RC. Here you have an internal emitter resistance REX. Very simple. Okay, this C. Now here you have a current gain factor GM times of V pi. Just correlate with what I said in the last slide. From the BJT I converted into the hybrid biequivalent expanded model. Then I have considered the resistance R0 between your collector and emitter. Then here you have a capacitance, that is a capacitance between the substrate and the collector terminal. Okay, this is your expanded model. This is your expanded model. Okay, so here what you want to understand is this RB will be very low value. This REX also will be very low value. This RC also will be very low value. This R mu will be more greater. Okay, the R mu will be more greater. Okay, that you want to remember because it's a reverse bias resistance. Okay, that you keep in mind. Okay, similarly this capacitance value also very less. This value will be very less. This value will be very less. This also will be less, and this also will be very less. This value will be very large. Okay, this capacitance value will be very less compared to this C pi. So because forward bias capacitance only will be large when you compare with the C mu, because it's a reverse bias part. This is a dependent current source and this is your early effect resistance. That's all. Now come to the model. See, this is what I said now. See, this is a network 1, this is a network 2, this is a network, this is a network 3. Just correlate with the last slide what I have discussed. Network 4, network 5, 4, network 5, network 6, network 7, network 8. That's all. So you'll get the expanded hybrid pi model. Okay, so this is a simple way to draw the higher frequency analysis of your BJT amplifier. The name is expanded hybrid pi model. Okay, from the expanded hybrid pi model, I am going to draw the simplified model. How I am going to remove this part. I am going to remove this one. I am going to remove this one, and I am going to remove this part. Going to remove this part. I am going to remove this part, and I am going to remove this part. Already I said these values RB, REX, RC values are very low, so need not to consider. All values will be negligible. This R mu will be very high, so the reactance will be larger, and this R mu will be considered as an open circuit in the higher frequency analysis because it is a resistance because of the reverse bias. So this R mu will be considered as an open circuit, so this also will be removed from the model. So this value, this also, everything will be removed from your circuit. Okay, after removing, you can see that. Okay, so you have a here the R naught is not removed. Okay, the R naught need not to remove now. Okay, so later while you are doing the short circuit part, that time we can remove. Okay, now you consider R naught. Okay, so what are the things we have removed? We have removed RB, REX, R mu we have removed because of the huge resistance. In the higher frequency part, it will act as an open circuit. Then CS is very low value, that is value very low, that also I can remove. RC also I can remove. So once you remove, you will be getting your simplified model. So you can see you will get this simplified model. So this is your model. Okay, so wherever I can see, I just encircle that part. This is your model. This is your model. So this is your simplified model. So this is your simplified higher frequency model. So what I am going to do now is I am going to do the short circuit current gain. What do you mean by short circuit current gain? I am going to short the load, and I am going to find what is the maximum current that can flow in the circuit. Okay, so what is the maximum current that can flow in the circuit? That I have considered as your output current IC and the input current as IB. So I am repeating again, I am going to short circuit the load, and I am going to find what is your maximum current that can flow in the circuit. What is the maximum gain I want to find? That is ratio of output current by input current, that is IC by IB. So while you short circuit this load, this R naught will be negligible because the resistance will be here you have a very you don't have any resistance in this short circuit part. You have a high resistance in this R naught, so this will be negligible. So current will not go to this path. Current will not go to this path. Current will go only the less resistance part. In that consideration, I remove from this equivalent model. So okay. So for a further analysis, you no need to take this R naught. Okay, the R naught will be removed. Okay, R naught will be removed. Now for this circuit, what I am going to find, you have to be very clear. I am going to find what is your current gain, that is your ratio of IC by IB. I am going to find what is the HFE, that is your objective of your this derivation path. Okay, see, I have input current IB, I have output current IC, I have short circuited. This is your simplified model for your common emitter BJT amplifier circuit. Higher frequency simplified model. Okay, not expanded one. Expanded means you will be having all values RB, REX, RC, then CS, then you have R, everything will be having that model. Okay, this is a simplified model. Here I am going to apply the KCL for this node. For this, if you consider this node, your IB current is entering here, your current across this path will be leaving. Okay, so that means IB equal to V pi by R pi, B pi divided by 1 divided by J omega C pi in terms of reactance. Similarly here V pi, see, you can see the C mu also dependent to this C mu capacitance, right? So V pi also dependent to this C mu capacitance. So V pi divided by 1 divided by J omega C mu. Okay, so now you rewrite this equation. So what you will get, V pi you take a common because you can see V pi is common in all all terms, right? So if you take V pi common, you will be getting 1 divided by R pi plus j omega. You take outside, you will get C pi plus C mu. So this is your updated equation. I hope you are clear up to this. Okay, we'll continue to this. What I am going to do is I am going to apply KVL in the output side. So when you apply the KVL in the output side, current is entering. From here the current is entering, current is leaving. So you apply KCL to this node. So what you will get? So IC plus you can see IC plus. So for this capacitance, how you will write? This is again this already said the cu mu is dependent to the input as well as output. Here I applied for input KCL with respect to the input port B. I have considered. Similarly, here I have applied the KCL for the output node. Here also I am considering, because it is a dependent for the both input part and the output part. So when you write with respect to output terminal C, how you write? That is V pi divided by 1 divided by j omega C mu, which is output terminal GM V pi. So this both are incoming. This is a outgoing current dependent source. Okay, this is outgoing. Okay, so now if you rewrite what you will get? V pi into j omega C mu plus IC equal to GM V pi. So now you rewrite the equation IC equal to V pi, you take outside, GM minus j omega C mu. I hope you are clear. From here, what I am going to do, I am going to find V pi. So just rearrange the equation. So V pi, and if you can rewrite like a V pi equal to IC. You bring this term down. So V pi equal to IC divided by GM minus j omega C mu. I hope up to this you are clear. Okay, now very interesting. Here you already determined the equation V pi equal to IC divided by GM minus j omega C mu. Okay, already we have determined the equation earlier slides, that is IB equal to V pi into 1 divided by R pi plus j omega into C pi plus C mu. Okay, so this both equation already we have determined in the earlier stage. What I am going to do is I am going to substitute this V pi here. Okay, I am going to substitute this V pi here, that's all. So if you substitute, you will be getting this equation. Okay, so what I want to get actually, I want to get, so what is the actual expectation for us? I want to find IC by IB, but you can take this IC down, you will be getting reverse of our expectation, that is IB by IC will be getting, but our requirement is IC by IB, so you want to reverse the equation. Okay, so we will do here. Okay, so what they have done here is, so I am repeating this equation again here for your continuation. Okay, so here what I have done is I have just change the IC and IB. This is our requirement, right? So IC by IB. So what you will get, this will go to the numerator and this will come to the denominator. So GM minus j omega C mu divided by 1 divided by R pi plus j omega C pi plus C mu. I hope you are clear up to this. Okay, so this is your HFE value. So this is a HFE value, that is your current gain which you obtained here. Okay, now I am going to make a few assumption. So listen to me. See, from this I am going to remove this factor. Because what the assumption is, GM is very greater than your C mu. Okay, if you consider this typical values, so C mu equal to 0.05 picofarad and GM equal to 50 milliamps per volt for 500 megahertz. Here another thing is, your transistor can work up to in the range of megahertz. It will not work in the gigahertz. Your small signal transistor maximum it can support in the range of megahertz only. Okay, so no small signal transistor will support to work in the gigahertz frequency. That you want to be very clear. So here they insisted GM is very greater than the omega times of C mu. So with that consideration, your GM is considered, and this factor is removed from this model, from this equation. So this equation is updated, right? So again I can take LCM. If you take LCM, this R pi will come here, and this R pi will go to the numerator. Okay, so your updated equation. So here you can see this after taking LCM. So you will be getting this R pi here will come, this R pi will go up, So we'll be getting gm r pi divided by 1 plus j omega r pi into c pi plus c mu. That's all. See now, very interesting mathematics. Gm r pi divided by 1 plus this omega I am writing as a 2 pi f into c pi plus c mu. I am considering the beta. What is f beta? You want to know what is f beta. See, consider this is your x-axis and this is your y-axis. So this is your magnitude graph and this is the phase graph. So in the magnitude graph, you can see the maximum gain, your magnitude you are getting like a beta naught. In the 3 dB frequency, you know it will be reduced by beta naught by root 2. That we want to prove. So there is, see, this is the cutoff frequency point. Somewhere after the frequency, the gain is you have a limitation in the gain. That part is called cutoff frequency. Okay, see, over the period different ranges of the frequency, one certain particular frequency, the gain is limited and it started to give the roll-off function. Okay, that particular frequency is called f beta. Okay, so in the x-axis the frequency and the cutoff frequency is happening at the f beta. Okay, so I am going to consider f beta I am going to assume like a 1 divided by 2 pi r pi into c pi plus c mu. Okay, if you substitute here, so this equation will be equivalent to this part. Okay, see, gm r pi divided by 1 plus j f pi f beta. What is f beta? This is f beta. If you substitute here, both the equations are same. I am correct or not? Gm r pi divided by 1 plus j f divided by 1 divided by 2 pi r pi c pi plus c mu. So in order to do my simplification, I rewritten this equation like this. I rewritten this equation like this. How? Gm r pi divided by 1 plus j f divided by f beta. So this is a final equation I am taking for further simplification. So by substituting this, you will get this updated equation. From this equation, both are same. If you substitute this f beta here, okay, this is written as a f by f beta after substituting this f beta value. Okay, so this is your phase representation. You can see here your input small signal current and output small signal current will be lag by minus 90 degree. Over the different ranges of frequency, you have a phase will be changed with respect to the input and output. That's what it is explained in this phase representation. This is a magnitude representation. Maximum gain is beta naught at the cutoff frequency. At the cutoff frequency, the gain is reduced by root 2 times. That we want to prove now. Okay, how we are getting beta naught by root 2. That we will prove. Okay, so what we consider is HF equal to gm r pi divided by 1 plus j omega r pi into c pi plus c mu. Here I am substituting j 2 pi f. Okay, by bringing this assumption here, I can write like a gm r pi divided by 1 plus j f pi f beta. Correct. So this equation was rewritten like this. Now I am rewriting this gm r pi as a beta. You know that the product of gm into r pi is nothing but your beta. Okay. So with that assumption, beta naught divided by 1 plus j f pi f of beta. If you take the modulus, what you will get? If you take a modulus for this equation, you will get beta naught divided by square root of 1 plus f divided by f beta whole square. So you know that this is the x-axis frequency. The gain is starting to reduce somewhere at the frequency of f beta. The ranges of frequency, somewhere it is starting to limit. That name is f beta. So I can substitute f in terms of f beta so that both will cancel. You will get HF equal to beta naught divided by 1 plus f beta will get cancelled because f I am writing as f beta. So both will get cancelled. So 1 plus 1, 2. So it will be written as beta naught divided by root 2. So that is f equal to f beta while you are considering. So final understanding is so you are at the 3 dB, your gain will be reduced by beta naught divided by root 2 times. Okay.